Welcome back, class. Today we're going to talk about the division algorithm. But before we get to talking about the division algorithm, I want to use this as an excuse to talk a little bit about the structure of mathematics more broadly. There are really two sorts of foundations on which mathematics is built. So we've talked about definitions before, and definitions are things we choose. If we want to define the word even or odd or whatever, we can just write it down as a definition. The other piece of the foundations here are what we call axioms. And axioms are simple statements that we choose to basically start with as building blocks to prove things. And ultimately in math, everything is proven from definitions and axioms. Now, most of the time, most people and most mathematicians don't encounter the axioms much. The axioms tend to be a bit technical, and usually the things we actually encounter are things that people have already derived from the definitions and axioms. So on top of the definitions and axioms, we build things that we call theorems. Most of the things you learn in a math class will amount to the definitions of the objects, the examples of things that satisfy those definitions, and then the theorems about those objects. So in this class so far, in most of the examples we've done, we've proven things by starting with a definition, deconstructing the definition, and then sort of putting the definition back together. So our main steps have been based so far on definitions. However, in a more advanced math class, it will tend to be that most of the steps will involve applying theorems. Today we're going to learn our first real theorem. And this theorem, for weird reasons, goes by the name the division algorithm. I'll make a comment at the end about why you would call this thing the division algorithm. But here's what it says. If we let a be an integer and b be a positive integer, then there exist unique integers, q and r, such that a is equal to b times q plus r, and r is between 0 and b, where notice I have a less than or equal to here, and a strictly less than here. So there are lots of things to say about this theorem. But before I say any of them, let me just do an example of applying this. So I would normally solicit here for you to shout out examples of numbers that you could pick, but I guess I will just have to pick my own numbers. I will pick a to be 37 and b to be 11. So here when I'm starting this theorem, it just says let a be an integer and b be a positive integer. So there's an integer, there's a positive integer. Okay, now there's supposed to exist q and r that satisfy this. So 37 is supposed to be equal to 11 times q plus r, and I'm supposed to have 0 is less than or equal to r is less than 11. So I want 11 times q plus r to be 37. I think by inspection, which is a fancy way to say I looked at it and guessed, we can find that we want q to be 3 and r to be 4, and these work for the theorem. Right? 3 times 11, or 11 times 3, I suppose I should say. 11 times 3 is 33, plus 4 is 37, and 4 is between 0 and 11. So this theorem is saying I can always do that, no matter what two integers I start with. I can always find a matching pair, q and r, where a is b times q plus r, and r is between 0 and b. Now, already you might be figuring out why the letters q and r were chosen here. They were not at all random. Really what happened here is that q here is short for the word quotient, and r here is short for the word remainder. And so What this is really saying here is, in the elementary school sense, if you divide 37 by 11, you get 3 with a remainder of 4. Next comment is that this theorem actually contains a new quantifier. Namely, it doesn't just say there exist Q and R, which is how I treated it in the example. It actually says there exist unique Q and R. And so this quantifier, there exists unique, is a combination of there exists, meaning there are integers Q and R, but then the unique part adds the caveat that there's exactly one such pair. So here's how I think of this. Imagine that I pick a new A and a new B. I will pick A to be 163 and B to be 7. Now what this theorem says is that I can find Q and R that will make this statement true. But not just that I could do it, you could do it too. And so you could imagine, and this might not be so difficult to imagine in this instance, that you and I might be in different rooms, and we might do this separately. When someone says there exists a unique something, the way I think it makes most sense to interpret this is if two people did this in separate rooms without talking to each other, they would always come back with the same answer. So, in other words, there's only one answer to this question. That's much different than the usual existential quantifier, because in the usual existential quantifier, we're just saying, well, there's at least one solution, but we don't care. There could be hundreds, there could be exactly one. We're totally indifferent with a usual existential quantifier. This is a much more restrictive quantifier. So why is this called the division algorithm? Well, there's a couple ways to prove it. But one way to prove it is to give a prescriptive way to produce this solution. And so I might want to know what 163 divided by 7 is. And in fact, we have an algorithm that is just a procedure, that's all algorithm means, for producing this answer, that is for producing Q and R. And so if you think about it, I can put this 7 here into the 16, again, just like we would do in elementary school. 7 goes into 16 twice. Okay, carry that, minus 2. 7 doesn't go into 2, so I drop down the 3. 7 goes into 23 3 times. 7 times 3 is 21. So that is 2. And so, in fact, just as you learned, again, in elementary school, this is the quotient, that's Q. This is the remainder, that's R. You can check. 163 is 23 times 7 plus 2. And this 2 is between 0 and 7, like so. So one way to prove the theorem that's known as the division algorithm is to prove that this procedure, in fact, produces a Q and an R that satisfy this requirement. It's a bit tedious, but it's doable. Now, the reason why at the beginning of this video I mentioned axioms is that ultimately all that argument that there's an algorithm that does this is to prove that there exist Q and R with this property. It doesn't prove that there exist unique Q and R with this property. To prove there exist unique Q and R with this property, you really actually need to dive deep into what the axioms for the integers or the positive integers actually are. And that's going several steps deeper into this than I want to go. So we're going to, from now on, take as given that the division algorithm is true. And you're going to be able to apply in any question you want the statement that the division algorithm is true. So hypothetically, if you ever have integers a and b that meet these requirements, then you can go ahead and use the division algorithm to produce integers q and r. Before we leap back into more applications of the division algorithm, and I explain why exactly it is that we're talking about it right now, let me give you an example of there exists a unique statement that you've probably seen before. So here's a true statement that uses this there exists a unique quantifier. Namely, there exists a unique real number x such that 2x plus 3 is 7. And I want to think about how you would go about proving this. Well, again, there's really two parts. One is to show the existence piece. So x equals 2 is certainly such an integer. And all that's saying is, well, 2 times 2 plus 3 is 7. But all we've proven here is that there exists a real number r such that this is true. Why is that real number unique? To prove uniqueness, we need to prove that if x is in R and 2x plus 3 equals 7, then x equals 2. In other words, we need to prove not just that 2 is a solution, which is pretty clear to start with, but we need to prove that 2 is the only solution. Well, what do we want to do? We want to suppose x is in R, and 2x plus 3 is equal to 7. Well, then what can we do? Well, then I can subtract 3 from both sides, so that will give me then 2x is equal to 4, and then divide both sides by 2, and I'll get so x is 2. In other words, assuming that x is a solution to this equation, we end up proving that x is 2. And so that establishes the claim that there exists a unique x in R such that this is true. To check your understanding, decide for yourself, is this true? There exists a unique x in R such that x squared plus 3 equals 7. And if you do believe it's true, then prove it. Well, there's two pieces, right, if we're going to prove this. The first is the there exists piece. What does the there exists piece look like? X equals 2 is such a thing. There's definitely a solution. What would part 2 be? Well, part 2 would be to prove that this is the only solution. So that would be to prove that if x is in R, and x squared plus 3 is 7, then x is equal to 2. So you could do that. So you suppose x squared plus 3 equals 7, and x is in R. Then x squared is 4, and you take the square root of both sides, and you get x is 2. And then you're done. But hopefully most of you at this point are screaming at your screen because what I've written down is completely wrong. Because it's not true that there's a unique solution to this. So this is all bogus. This statement is just completely false. Why is it false? It's false because, yes, x equals 2 is a solution, but so is x equals minus 2. So yes, there exists a solution to this equation, but it is not unique. So what went wrong? I wrote down a proof and put a proof box and everything. How could it possibly have gone wrong? Well, what went wrong is I went from x squared equals 4 to x equals 2, which is basically me saying, oh, well, I'm just taking the square root of both sides. However, taking the square root of both sides is not a supported operation of an equation. It's not true that if x squared equals 4, then x equals 2. Because, well, x could just as well be minus 2. And so if you remember from when you took algebra or calculus or whatever, whenever you had this x squared equals 4 business, you were supposed to then say, so x equals plus or minus 2. And there was always this mystery of where exactly the plus or minus came from or why it was there. This is really why it's there. So this really goes to show you the difference between there exists a unique something versus just there exists something. Okay, and in this case, there exists a unique solution to 2x plus 3 equals 7, whereas there exists a solution to x squared plus 3 equals 7, but it's not unique. This warrants one further aside before we leap back to talking about the division algorithm, which is what happens when you solve an equation. That is to say, logically, what's happening? So let's go way back to something that you would have done in like Algebra 1, and let's solve the equation x times x plus 1 equals 20. Logically, what are we doing? Really, the first thing we're doing is we're supposing that x is such a solution. Now, this actually might seem a little bit backwards, but bear with me, this is going to explain some of the weird stuff you've seen happen with equations over the years. But let's start by supposing we have a solution. Well, then once you've supposed you had a solution, well, then you can sort of continue to do algebra stuff. And so again, as long as this original equation is correct, this equation's correct, and this equation's correct, and then it's not so hard to see that we can factor this. And now you probably haven't thought about this in a long while, but we actually make a rather cute leap of logic here, which is to note these two numbers multiply together to be 0, and so the only way for that to happen is for one of those numbers to be 0. And so we go from this statement to the statement x plus 5 equals 0, or, and this is just our friend or, x minus 4 equals 0. This is just the plain old logical or. And thus, simplifying that just a smidge, we get x equals minus 5, or x equals 4. And so what is it we've really proven? We've really proven here that if x is in R, and x times x plus 1 equals 20, then x equals minus 5, or x equals 4. Now, if this reads a little oddly to you, it's because this isn't even really what I wanted. I really wanted to know that x equals minus 5 and x equals 4 were solutions. But when I quote-unquote solved the equation, that's not even what I actually learned. Okay. Let me do one more example and show you why that matters. So let's now solve for x in this equation. And again, let's be careful about the logic here. So we're going to suppose that x is a real number, and the square root of x plus 4 is equal to x minus 2. I can then square both sides. And so I'll get that x plus 4 is equal to x squared minus 4x plus 4. Now move everything over. So x squared minus, and then this will be minus 5x equals 0. So x times x minus 5 equals 0. And so, by our logic, x is 0 or x minus 5 is 0. And so, x is 0 or x is 5. And so what have we proven here? We have proven here that if x is a real number, and the square root of x plus 4 is x minus 2, then x is 0 or x is 5. Let me muddy the waters just a little bit here. Let's plug in x equals 5. When I plug in x equals 5, I get the square root of 9 is equal to 5 minus 3. That is, I get 3 equals 3, which is great. When I plug in x equals 0, though, what do I get? I get the square root of 4 equals minus 2. That's not right. 0 is not a solution to this equation. Does that mean our proof was wrong? Well, no, it doesn't, because this if-then statement is true. It just so happens that if x is a solution to this equation, it never happens that x is 0. In fact, what's actually true is that if x is a solution to this equation, then x is 5. Our logic here was impeccable. Everything we proved was correct, but we didn't actually answer the question that we probably wanted to answer. And so you might remember, this thing is called an extraneous solution. That is to say that this thing is something that popped out of our algebra, but then when you actually go back to the original equation, it doesn't work. And the reason why extraneous solutions can happen is precisely that when you're solving an equation, you're really following a sequence of starting with supposing you have a solution and then deducing things that have to be true about it. But there's no part of the logic that then would imply that just because you get to this, that thing would actually work. And so, in fact, sometimes it will happen in equations, particularly when they involve square roots or logs or other things of that sort, that you do this logic and you follow it through to the end and you get some solutions, but those solutions aren't actually solutions. Again, this all comes down to the actual logic that is following solving equations. Thus, as a final note, what we've actually proven is that there exists a unique x in R such that that equation is true. Namely, it's 5. And if you look through our proof and look at the fact that we showed that all solutions have to be 5 or 0, but 0 isn't actually a solution, then we've really proven this statement. From there, after that aside about solving equations, let's go back to talking about the division algorithm again. So reminder, what does the division algorithm say? Well, the division algorithm says this. Namely, it says this statement about how no matter what integer and positive integer I pick, I can always find a unique quotient and remainder that will make this statement true. Namely, that it should always be the case that there's a unique number q and a unique number r that's in this bound, such that a is equal to b times q plus r. So, one of the most common ways we're going to apply this theorem is to apply it to a specific b. So, let's see what happens if we apply this to b equals 2. If I apply this with b equals 2 specifically, then what does this say? This says if a is an integer, then there exists unique integers q and r, such that a is equal to 2q plus r, and r is between 0 and 2. Now I want to do a little bit of rewriting of that statement. Namely, this piece here, well, r is an integer, so this is really saying that r is 0 or r is 1, right? Those are the only integers that are between 0 and 2 where they're strictly less than 2 and greater than or equal to 0. So now since r is always going to be 0 or 1, I can break those two pieces out and say that there exists a unique q such that a is 2q or a is 2q plus 1. Now, in fact, because the r is unique, not only is this an OR, in fact, this is an exclusive OR. Okay, this is by uniqueness. And so if I really squint at this, what I'll actually see here is, well, if I say a is 2q, what am I really saying? I'm really saying a is even. Or, if a is 2q plus 1, I'm really saying A is odd. These are in fact exactly our definitions of even and odd. There exists a Q such that A is 2Q, that's even. There exists a Q such that A is 2Q plus 1, that's odd. And so at the end of the day, what did we really just prove? We really just proved that if A is an integer, then A is even, XOR A is odd. And now if you have a particularly good memory, you might remember that when we defined even and odd, I had to make this note that integers that aren't even are odd, and integers that aren't odd are even, even though those statements did not follow from the definition. You cannot prove directly from the definition that if A is an integer and doesn't look like 2Q, then it looks like 2Q plus 1. At least not easily. Really, in order to prove those things, you have to actually dig back into your definition of what it means to be an integer, which requires looking back into these axioms, which we'd prefer not to. However, we no longer have that problem. We now have the division algorithm that we can quote, and so as long as you believe the division algorithm, you now believe that every integer is even or odd. Probably you already believed that, but now you hopefully even more believe that. Now, typically in math, we would call this a corollary. What's a corollary? A corollary is a result that follows pretty easily from a big theorem. So in particular, a corollary is a true thing, so it's kind of a theorem itself. It's no less true than a theorem. But if we call it a corollary, we're saying, okay, this is a little result that we get out of the big result. And in this case, it's a little result that we got out of the big result of the division algorithm. Now, most often we're going to be applying the division algorithm for small integers that are bigger than 2. So 3, 4, 5, 6. These things are all fair game. And I want to look through what that looks like, what it tells us, and how we'd apply it in some various proofs. So here's our division algorithm if b is 3. This just says, for every n in the integers, there exists unique q and r in the integers such that n is 3q plus r. And this is really the driving force of the division algorithm, this r happens to live between 0 and 3. And so that's really saying r is 0, or r is 1, or r is 2. Those are the only possibilities. So here's how I would really interpret this. I would really say that when it comes to dividing by 3, there are 3 flavors of integers. The ones that look like 3q, the ones that look like 3q plus 1, and the ones that look like 3q plus 2. Namely, these are the 3 flavors. There's the flavor that looks like 3q for some q and z, the flavor that looks like 3q plus 1 for some q and z, and the flavor that looks like 3q plus 2 for some q and z. And I want to remind you, because of the uniqueness, there's no integers that accidentally fall in 2 of these. So every integer is exactly one of these flavors. So I tend mentally to think of these things as buckets. So when I apply the division algorithm with b equals 3, what I learn is that the integers all fall into exactly one of these 3 buckets. The 3q bucket, the 3q plus 1 bucket, and the 3q plus 2 bucket. And so if you pick your favorite integer, like 11, for example, you can ask yourself, okay, where is 11 in this list? And 11 would be in the 3q plus 2 bucket, because 11 is 3 times 3 plus 2. So this would be the bucket that contains 11. What about 45? Well, 45 is 3 times 15, so that would mean 45 is just in the 3q bucket, and so on. So in a way, even and odd are all about what happens when you divide by 2, but sometimes we want to think about dividing by other numbers. And so when we divide by 3, for example, we learn that instead of there being 2 flavors, even and odd, there's actually these 3 flavors. Now, one thing I want to address is the fact that you very often see people talk about how weird it is that 2 is the only even prime. And I just want to point out that on one sense, yes, that's cute, and you get to make puns about how it's odd or whatever. But on the other hand, it is completely non-mysterious, because even means divisible by 2. And so, of course, the only prime that's divisible by 2 is 2, because primes aren't allowed to be divisible by things. If you were forced to think about it, well, this is kind of the bucket that's most like even. If you were forced to, you could call this bucket the Threven bucket. And, well, how many primes are in this bucket? Well, 3 is the only prime in here because all the numbers in this bucket are divisible by 3. And so, in fact, 3 is the only prime divisible by 3. Equally well, 5 is the only prime divisible by 5, 7 is the only prime divisible by 7, and so on. All of these are really the same statement as saying that 2 is the only even prime. It just so happens that we think about even and odd more than we're used to thinking about these buckets or the mod 4 buckets, the mod 5 buckets, and so on. So how do we use this? We use this quite often when we want to prove statements about divisibility. So here's a sample statement. Prove that if I start with an integer n, and n is not divisible by 3, then n squared minus 1 is divisible by 3. So I'm going to proceed here by direct proof. And so I'm going to suppose that n is in Z and n is not divisible by 3. And now, if I didn't know the division algorithm, I'd be kind of stuck, because the hypothesis n is not divisible by 3 is very unhelpful. It says something like, for every integer k, n is not equal to 3k. Well, that's not going to be super nice. But by the division algorithm, n has to belong to one of these 3 buckets. However, if n is not divisible by 3, then that's exactly saying that n is not in this bucket. So what bucket is it then? Well, it's in one of these 2 buckets. And so we can follow up. By the division algorithm, there exists q such that n is 3q plus 1, or n is 3q plus 2. The reason why this is so useful is that instead of saying something that n isn't, it lets us turn this into something that n is. Namely, we get to say n is equal to 3q plus 1, or n is 3q plus 2. And from there, we can do a lot more. Namely, what I'm really going to do here is something that we're going to call proof by cases eventually, which is to say, okay, there's 2 possibilities. I'm just going to look at those 2 possibilities. So if n is 3q plus 1, then n squared minus 1 would be 3q plus 1 squared minus 1, which would be 9q squared plus 6q plus 1 minus 1, which would be 9q squared plus 6q, which would equal 3 times 3q squared plus 2q. And then this is definitely a multiple of 3, because I've written it as 3 times an integer. So that handles that possibility. Now let's nail down this other possibility. So very similarly here, if n is 3q plus 2, then you can calculate that n squared minus 1 is 3q plus 2 squared minus 1, which works out after some algebra to be 9q squared plus 12q plus 3, which is 3 times 3q squared plus 4q plus 1, which is visibly a multiple of 3. And so having checked both of these cases, that is, having checked both of the possibilities of this OR, we've now checked all the possibilities, and so this statement is true. If you take any integer that's not a multiple of 3, square it, and subtract 1, you'll always get something that is divisible by 3. And this is exactly the power of the division algorithm. We've often on the homework seen phrases pop up like, if n is even, but not a multiple of 4. And even but not a multiple of 4 unto itself is not a super helpful description. Again, because it's really complicated and involved. But if we think about this in terms of the division algorithm, and what the division algorithm guarantees for us, this actually says something rather clean and nice. So if we divide by 4, what does it say? Well, we're going to fall into one of 4 buckets. Either multiple of 4, multiple of 4 with remainder 1, multiple of 4 with remainder 2, multiple of 4 with remainder 3. So here are our 4 buckets given to us by the division algorithm. So if n is even but not a multiple of 4, which bucket is n in? Well, this bucket is a multiple of 4. So it's not this one. These things are all multiples of 4. On the other hand, 4k plus 1, that's odd. So not in that bucket, those things are odd. Likewise, things in this bucket are also odd. Okay, so not in that bucket. So this phrase, if n is even but not a multiple of 4, you can actually rewrite that. That actually means the same thing as n is of the form 4k plus 2. This kind of translation is something that you'll become fairly expedient at as you practice doing the questions associated with the division algorithm, and particularly this is going to come up a lot in the next section. That's all for now. In the next video, we're going to talk about using the contrapositive to do proofs. But that's all for now. I'll see you next time.